architectural wonders of microprocessor, and execution of programs using 8051 microprocessor. Is it 8051 microprocessor? No, it is 8051 microcontroller. Okay. Why it is given as 8051 microprocessor means the microprocessor present inside the 8051 microcontroller. That is what the meaning here. Okay. So let us start with a very interesting transistor part, which you can enjoy. It's a good way to start, and it is a good celebration for us, all of us today. If you look at this, this is a transistor. This is the transistor, which is not biased, which is very important. So transistor can be biased, and the transistor can be unbiased. So this is an unbiased transistor. Why? Because there is no voltage divider bias, there is no collector to base bias, and there is no, it is not biased. So if the transistor is not biased, as we all know, it works in the cutoff region and saturation region. Here you can see the input is A. The transistor is biased, it's not biased. So the input to the transistor is A, and the output to the transistor is Q. So when we look at this, if the transistor is not biased, it acts as a switch. When the transistor is not biased, it acts as a switch. So how it acts as a switch means, so here there is a supply, VCC is a supply, and this is the output. So when the input A is 0, that means when we are not giving any input to the base of the transistor, so the transistor acts as an open switch. The transistor acts as an open switch. When the transistor acts as an open switch means the resistance will be infinity. When the resistance is infinity means, then automatically there will be a maximum potential drop across this infinite resistance. Hence, if you measure the voltage across this, the voltage will be VCC. So VCC is voltage connected to collector, because this is the collector of the transistor. So the voltage connected to collector is 5 volts, say for example. 5 volt will come in the output. Okay. So when A is 0, then output Q is 5 volts. 5 volts in the sense logic 1. 5 volts is logic 1 and 0 voltage is logic 0 with respect to TDA logic, as we all know. So let us say, look at this small table here. When A is 0, the output is 1. So when you give A as 1, 1 means what? Again 5 volt here. So when A is 1, so this base emitter junction is forward biased, and this acts as a closed switch. Closed switch means what? It acts as a closed path for the current to flow. Hence, the potential difference across the closed path is 0, as we all know. So when the A input is 1, the output is 0. When A input is 0, the output is 1. It's fantastic, right? So when A is 0, the output is A bar. When A is 1, the output is A bar. So the input is A, output is A bar. Here it is Q is not Q bar, it may be A bar. We can say like this. And the truth table here, which shows clearly when A is 0, the output is 1. When A is 1, the output is 0. It's fantastic, right? So transistor acts as a switch when it is not biased. Much better if I want to say, when A is 0, transistor acts in cutoff region. Transistor is in cutoff region. And when A is 1, transistor is in saturation region. Something like that we can say. And finally, the moral of the discussion is, this table is a truth table for a NOT gate. Do you agree? When input is 0, output is complemented as 1. When the input is 1, output is complemented as 0. It's fantastic, right? So an unbiased transistor acts as a switch which behaves like a NOT gate as shown. Is it clear or not? Your transistor can become a gate. That is the moral of the story. Transistor as a switch becomes a NOT gate. This is very, very, very important for us. So from this understanding, we normally, when we say an integrated circuit, means we talk about small scale integration, medium scale integration, large scale integration, ultra large scale integration. So normally we used to say several million transistors are inside the microprocessor or microcontroller, etc. So several million transistor means each transistors are behaving as a switch. That is the one we need to understand. And that switch can be treated as a gate as per this discussion. So the transistor which is acting as a switch, and according to this connection, we can make use of this transistor as a NOT gate. That is very interesting. Okay, so that is the one we need to understand. So coming to the next circuit, the transistor can be connected in both ways. Transistor can be connected in series and transistor can be connected in parallel. So this is the series connection of two transistors. Yes or no? This is the series connection of two transistors. Series connection means between VCC and ground, transistors are connected in series. Okay, so the supply voltage is coming through the resistor, and there is it has to pass through the transistor 1, it has to pass through the transistor 2, and then it closes the circuit. So this is the closed path. So this is the path for the current to flow, and here there are some two inputs, which is A and B, and here there is one output, which is Q. So this is very interesting here. When we connect the two transistors in series, as per the earlier discussion, when both A and B are 0, there are two switches which are in off state, hence maximum resistance will be there, then output will be logic 1. So if you see both A and B are 0, the output is logic 1. Why? Because there will be a maximum resistance. When A is 1, this transistor will be on, and this acts as a closed switch, and this transistor is off, this acts as an open switch, and even now the current will not flow through the transistor because there is no closed path, because this transistor B is in off state, hence we are getting logic 1 in the output as shown in the second row of this table. So when we make B as 1 and A as 0 means, so this transistor acts as an open circuit, this transistor acts as a closed switch. So if any one of the switches is open means again the current will not flow because it is series connection. Hence when A is 0, B is 1, or when B is 0, A is 1, in both the cases the current will not flow through these transistors. Hence the output is logic 1 way because maximum resistance will be there. So when both the inputs A and B are 1, both the transistors will be switched on, and this acts as a closed path for the current. Hence the voltage across the closed path will become 0, hence the output is 0. So when both the inputs are 1, the output is 0. This is fantastic. So, but you look at the table, this is the truth table for what? 0, 0 means output 1, 0, 1 means output 1, 1, 0 means output 1, and 1, 1 means output 0. So this is the truth table for NAND gate. So when the two transistors connected in series, it behaves like an AND gate as shown here. It's fantastic, right? So series connection of two transistors becomes NAND gate. Beautiful. Clear? So transistor acts as a NOT gate. Transistor can be either connected in series or in parallel. When the two transistors are connected in series, it behaves like a NAND gate according to this discussion. Now we are trying to connect the transistors in parallel because this is the only possible combination. Transistor can be either connected in series or it can be connected in parallel. When we connect the two transistors like this, it behaves like a NAND gate. When we connect the two transistors parallelly means this is how it has to be connected. When the two transistors are connected in parallelly, then what happens? When both the inputs are 0, as per the discussion, the output will be in logic 1 state. If any one of the transistor is 1, but any one of the input is 1, if A is 1 means the current will flow through this transistor and then it will be grounded. Current will flow through this transistor and then it will be grounded. If B is 1, the current will flow through this transistor and then will be grounded. And both the inputs are 1. Again, current will flow through both the transistors and then it will be grounded. Here in this case, when A and B are 0, then only their output is 1. If any one of the input is 1, the output is 0. That is the idea here. So this is the truth table, or this is the truth table for a NOR gate. Fantastic, right? It's NOR gate. So when the two transistors are connected in parallel, it behaves like an OR gate. When the two transistors are connected in series, it behaves like a NAND gate. Hence, NAND gate and NOR gates are called as universal gates. Fantastic, right? This is what you have learned in digital electronics. So while learning digital electronics, we have discussed that NAND and NOR are the universal gates. Why? Because transistor is the basic building block of all the integrated circuits. So transistor and act as a switch means it acts as an OR gate. Fantastic. And the possible interconnection of transistors are only either series or parallel. When the transistors are connected in series, it behaves like a NAND gate. When the transistors are connected in parallel, it behaves as an OR gate. This is the only possibility. Hence, NAND and NOR are the universal gates. Like this, we can celebrate this subject. So the parallel connection of two transistors becomes NOR gate. It is beautiful. Now, with gates, what we can do? So from up to this discussion, what we have understand, the transistor which is acting as a switch can act like a NOT gate, individual transistor. When we use two transistors, when they are connected in parallel, it acts as an OR gate. When they are connected in series, it acts as an AND gate. And with the combination of NAND gate and NOR gate, we can make XOR gate, we can make AND gate, we can make OR gate, and any kind of gate we can make, because this is called as universal gate, as we all know. Okay, what is the use of gate? Now the transistor can become gates with proper interconnection. With gates, what we can do? Now the next question comes. With gates, what we can do? With gates, we can make the gates to perform the operations. What operations we can do? Addition operation. How the logic gates can do addition operation? Let us look at it. So I hope you know the answer. How the logic gates can do addition operation? This is what you have done in digital electronics. You can see half adder. Yes, sir. Half adder. What is half adder? The combination of XOR gate and AND gate is an half adder as shown. So because it adds the two numbers. Fantastic, no? So binary adder. So logic gate is performing addition operation. So the output of the XOR gate is sum and the output of the AND gate is carry, as we all know very well. So when A and B are 0, the sum is 0 as well as carry is 0. When B is 1, the sum is 1 and carry is 0. When A is 1, sum is 1, carry is 0. When both the inputs A and B are 1, the sum becomes 0 and carry is 1. This is fantastic and beautiful inaugural function for microprocessors. Okay, so the interconnection of gates like this can perform addition. That is the moral of this discussion. As we all know, half adder is designed using XOR gate and AND gate, as shown. Half adder is using logic gates. That is, transistor becomes gate. Gates are performing the addition operation. Fantastic. Now, this is 2-bit addition, right? Now, when we go for 3 bits, when we combine these two half adders, it will become full adder. Yes or no? When we use 2 half adders like this, it will become 1 full adder. Along with OR gate, we can get carry out. So this circuit connections and everything we all know very well. But our interesting thing is the combination of different interconnection of gates becomes full adders. So this is a single bit adder or 2-bit adder, something like that we can go, because bits are the digital. So ones and zeros can be added. That confidence we got by using this circuit diagram. So full adder circuit is obtained using 2 half adders as shown. Now, still when we extend this, when you use such 4 full adders like this, then it will become 4-bit adders. Fantastic. When we use 4 such full adders like this, it will become 4-bit adders. So you can see A0, B0, A1, B1, A2, B2, and A3, B3 are the inputs, where S0, S1, S2, S3 are the outputs, and the carry is getting propagated like this from right to left. This is very important. So you can see 4-bit adder circuit is shown where A3 to A0 and B3 to B0 are the inputs, and S3 to S0 are the added sum. So for 8-bit processor, we need 8 such adders. For 16-bit processor, we need 16 such adders. And for 32-bit processor, 32 adders are needed. Beautiful, right? So this is 4-bit adder. Now you can see addition is over. Now let us try to do the subtraction. How to do subtraction? Which is very interesting. Subtraction can also be done using addition, as we all know, by using 2's complement addition. Is it clear or not? So when you look at this diagram, 2's complement addition is subtraction. We are interested to subtract 2 from 6. So 6 minus 2 is 4. Just I am refreshing all digital electronics what you have learned. So the binary equivalent of 6 is 0, 1, 1, 0. Look at the screen, look at the cursor. The binary input for the 6 is 0, 1, 1, 0. And the binary input for the 2 is 0, 0, 1, 0. And the answer is 4. 6 minus 2 is 4, 0, 1, 0, 0, which is 4. So how this can be arrived? This can be arrived by 2's complement addition. As we all know, 6 is 0, 1, 1, 0. And we have to take the 2's complement of this subtracted value. 0, 0, 1, 0 is the one value which has to be subtracted. 0, 0, 0, 1, 0 is the value which has to be subtracted. So that value you have to take it. That value you have to take it. That's 0, 0, 1, 0. You have to take the 1's complement of it. So 0 will become 1, 1 becomes 0, 0 becomes 1, 0 becomes 1. So 1, 1, 0, 1 is the 1's complement. So 1, 1, 0, 1 plus 1. We are adding 1 to this. So 1 plus 1 is 0. That is 10, so that is 10, 1. And this one comes down, this one comes down, so 1, 1, 1, 0. So 1, 1, 1, 0 is the 2's complement of this 2. So this we can add with 6. So 0, 1, 1, 0 is 6, and 1, 1, 1, 0 is 2's complement of 1, 1, 1, 0 is 2's complement of 2. So now if we add this, 0 plus 0 is 0, 1 plus 1 is 10, so 10 means 0 and there is a carry 1. So 1 plus 1 plus 1 means 11, so 11, 1 means again the carry 1, so 1 plus 1 is 0 then. So there exists a carry. So when there is a carry, then we can say, we can discard it and we can say that 4 is answer, 0, 1, 0. So discard the carry and then we can answer is getting 4. So the moral of this discussion is 6 minus 2 is 4. This 6 minus 2 is 4 is obtained. 6 minus 4 is obtained just by 6 minus 4 is obtained just like that by adding. So subtraction is done through addition. That is the moral of the story of this discussion. So look at the screen. From this example, it is clear that addition and subtraction is possible through adder itself. Is it right? Addition and subtraction is possible through adder itself. Repeated addition and subtraction is multiplication and division. Hence, it is possible to perform arithmetic operations like addition, subtraction, multiplication, division just by adder itself. Beautiful, fantastic. This is what you have to celebrate with digital electronics. That's what every time I used to say. Programmable digital electronics is microprocessors and microcontrollers. This is very, very important. Hence, the title for the slide is beautiful. Subtraction through addition. Yes, we can perform the subtraction through addition. This is beautiful. And repeated addition becomes multiplication and repeated subtraction becomes division. So addition, adder alone is more than enough. So with adder we can perform subtraction. Multiple addition can become multiplication. Multiple subtraction will become division. So the entire arithmetic operations can be done just like that by using adder itself. That is the moral of the story. So once again, to summarize our entire discussion, programmable digital electronics is microprocessor. This is the digital electronics what we have seen so far in your previous semesters. But here, this digital electronics is becoming programmable. This digital electronics is becoming programmable. Because this digital electronics is programmable, hence this is called as microprocessor. How this digital electronics becomes programmable, that is what we are going to see now. So as we all know, ones and zeros are going in and ones and zeros are coming out from the microprocessor. With ones and zeros, we can perform only addition and subtraction. Repeat addition becomes multiplication. Repeated subtraction becomes division. Hence, we can perform addition and subtraction, multiplication, division with ones and zeros. These operations are called as arithmetic operations. And coming to the logical operations, because the logic gates itself is performing logical operations. So with ones and zeros, we can perform only arithmetic and logical operations. With ones and zeros, we can perform only arithmetic and logical operations. So already we have seen how to perform arithmetic operation, and as we all know, logic gate itself is performing logical operations. So we need a module which can perform arithmetic and logical operations inside the microprocessor. Hence we can call ALU. ALU is the only element. So with ones and zeros, we can perform only arithmetic and logical operations. The module which performs this arithmetic and logical operations is called as arithmetic logic unit. Fantastic. It's beautiful. Hence, ALU is the processing element inside the microprocessor. It's fantastic, right? So now we are coming in depth. So the combination of this full adders and logic gates becomes arithmetic logic unit, which is the processing element inside the microprocessor. That we must know. It is fantastic, right? So arithmetic and logical operation. Now you can see, if you say 8-bit processor means processor has 8-bit ALU. Say for example, now we are using Intel Core i9 processor, which is a 64-bit processor. Hence we can say this is 64-bit ALU. That's all. So all of us are sitting in front of PC means we are using Intel Core i9 or i5 processor, i5 processor, which is a 64-bit processor. That means it has a 64-bit ALU. Just now we have seen the 4-bit ALU. Similarly, there is a 64-bit ALU. That's it. So 10th generation Intel Core 9 processor series link. Okay, so this is just to look at the Intel Core, and 8-bit processor has 8-bit ALU and 64-bit processor means it has 64-bit ALU. So this is just for you to understand, because today, because of the processors, all wonders are happening. Because of the processors, all wonders are happening. Because of the processors, all wonders are happening. Hence, we are using the most advanced processor, which is Core i9, and that is also a microprocessor. So the inaugural function is with 8085, 8051, what we are doing it right now. But the destination is Intel Core i9, which is the most extreme wonderful processor with respect to desktop. And that's why I'm given this slide, just for our understanding. Here you see that is 64-bit. So the Intel Core 9 is a 64-bit chip. Intel Core i9 is a 64-bit chip, and which is coming under the category of microprocessor. So Intel Core i9 is the specification is this, and this is this feature shows it is a 64-bit processor. Hence we can say it has a 64-bit ALU. That's it. Very interesting thing to discuss. Okay, so now processor is doing some process. What process it does? It does arithmetic and logical operations. How it does arithmetic and logical operations? It performs arithmetic and logical operations only through ALU. That is the one we need to understand. So ALU block has come into picture now. Yes or no? To perform 8-bit addition through ALU, we need two data. To perform 8-bit addition through ALU, we need two data. Data need to be stored somewhere inside the microprocessor. To perform 8-bit addition through ALU, we need two data. Data need to be stored somewhere inside the microprocessor. Hence, there is a need for storage element inside the microprocessor. As we all know, so ALU can perform arithmetic and logical operations. To perform arithmetic and logical operations, we need some data. Data has to be stored somewhere, no? That is very important. Where to store, how to store, that was discussed already, as we all know. Where to store and how to store, that was discussed already, which is flip-flop, as we all know. So this slide I have brought it here because flip-flop is also made up of logic gates. This we have already discussed because flip-flop is already made up of logic gates. This is for you to just quickly to refresh. So gates becomes flip-flops, which becomes the storage element called registers and memory. So logic gates is also doing the processing. Logic gates are also doing the storing purpose. So for storage also we use logic gates. For computation also we use logic gates. The basic building block of logic gates are transistors. Hence, transistors are the basic building blocks of microprocessors and microcontrollers. That is what we have discussed very clearly. It's fantastic, right? So gates is a storage element. This is just to understand, because we all discussed about the storage element, which is the D flip-flop, and this is the D flip-flop internal structure, which is made up of logic gates, which is very important, and its truth table is this. This we all know. Not necessary to concentrate much on this. Hence, now it is very clear. Look at this diagram, which is very important. So there is an arithmetic logic unit, and with the help of D flip-flops, there are registers. The storage element inside the microprocessor is called as register. So there is an accumulator register, which is called as A register, and there is a temporary register, which is internal some temporary registers. So one of the data to be added must be stored in accumulator. Another data which is to be added is in temporary register, and both data will be added by ALU, something like that we have to understand. This is the internal architecture of 8085 microprocessor, because when we learn microprocessor means we should start with 8085. So quickly we are refreshing that. So look at the screen. The storage element inside the microprocessors are called as registers. Fantastic. So this is the register structure of an 8-bit 8085 microprocessor. So register structure means what? You have an accumulator and you have temporary registers to store the data to be processed. So you can see accumulator is a register which holds one of the data to be processed and also the processed result. Okay, so one of the data to be stored, one of the data to be processed must be stored in accumulator, and the processed data is again will come back to the accumulator only. Okay, I will see some example you can understand. So accumulator is one of the register which holds one of the data to be processed, and also it stores the processed result. So from temporary register, the second data will come for processing as shown. Is it clear? So now this, if you observe this carefully, ALU is the processing element. For processing elements, we need the data to be processed. So data to be processed is available in the storage element called registers, because the registers are the storage element inside the microprocessor, which is made up of flip-flops. That we must know. It's fantastic. Now we see some good example, right? So 8-bit ALU for 8-bit processing. That is the title. So accumulator is one of the register, temporary register is another register. Now let us do the same example. How 8-bit ALU is performing. addition. So 8-bit ALU for 8-bit processor. So the processed result is stored back in the accumulator as shown. So the processed result is stored back in the accumulator as shown. So this is when you perform addition, 2 plus 4 equal to 6. Let us see how the ALU is performing addition from this diagram. When you see, let us assume that we are performing addition. So that means we are supposed to do addition. So one of the data is 2, another data is 4, and which has to be added, and the sum is 6. So what if you want to add two numbers means one data has to be stored in accumulator, another data has to be stored in temporary register. So one data has to be stored in accumulator means what? The 2 has to be in accumulator, say for example, and the 4 has to be in temporary register, say for example. So 2 and 4 are the two data which is in the accumulator and temporary register. It goes inside the ALU. It goes inside the ALU. So as we all know, it is an 8-bit adder which is present inside the ALU. So which performs 4 plus 2 equal to 6. And the sum will come through this way. The sum will come through this way, and then it will reach the accumulator. Because as discussed, one of the data to be processed, and the processed result is coming back to the accumulator. So by overwriting this input to the sum, 6 will be loaded as shown. It's very important. So already there one of the data to be processed is 2. It was overwritten as 6 as discussed here. So this is how a microprocessor is performing one arithmetic operation. It is applicable for 8-bit microprocessor as well as it is applicable for the microprocessor sitting inside your mobile phone, sitting inside your CPU, sitting inside your laptop. Here we are seeing one 8-bit addition. Like this, several crores and crores and crores and crores of operations is happening, but in the same way. That is the only thing you need to understand. Now you are more comfortable in understanding the internal operation of microprocessor. Now the question comes to our mind. Now we are very much happy that okay, this is how ALU is performing addition. Now let us go in depth. The process result is stored back in the accumulator as shown. The process result overrides the accumulator content, that is 02 to 06. The process results must be taken out from the accumulator only. So from the accumulator, only we have to take out the data. So before processing, one of the data to be processed must be kept in accumulator. After processing, you have to take out the data only from the accumulator. That is very interesting and it's very important. So after taking out from the because this is a storage element inside the microprocessor, we have to keep it inside the memory. That is copying from the accumulator and then we have to paste it into the memory. So that's what shown in the last row. So this result needs to be stored in the memory for the user to read it, because from the memory only we have to read, no? So we have to bring out the result from the accumulator to the memory. That is what we are going to do. That is what we did in the previous classes. Hope you understand. Now the question comes, how ALU knows I need to add? This is very important. How ALU knows I need to add? From the instructions. The answer is from the instructions. From the instructions, ALU knows I need to add. Now the question comes, what is an instruction? What is an instruction? Instructions are the command that we give it to the processor to do the necessary task. So instructions are the command that we give it to the processor to do the necessary task. Where will these instructions are available? These instructions are stored in the read-only memory as discussed. So we have to store the instruction like, okay, one of the data is available in accumulator, another data is available in temporary register. So add these two data and store the result in accumulator like that. We have to instruct the accumulator now. So which is called as instruction. We have to instruct the ALU, no? That is why it is called as instruction. Those instructions are stored in ROM, and those instructions need to be fetched from the ROM, and then it has to be decoded to understand I have to add two data. That is very important. How to bring the instructions to the microprocessor? Instructions are fetched from the memory and kept it inside the instruction register. Instructions are fetched from the memory and kept it inside the instruction register. So far we have seen how it performs addition, and before performing addition it should know there are two data in accumulator and temporary register. I need to add. How do ALU knows that I need to add two numbers? From the instructions. So where those instructions are there? Instructions are in ROM. And how ALU knows? So there is something like instruction register we need to understand. So there is something like instruction register inside the microprocessor. Okay, so what we have seen is this portion, accumulator, temporary register and arithmetic logic unit, this left side portion. But in the right side there is one instruction register you can see. So this is very important. So the register inside the microprocessor which is used to store the instruction is called as instruction register. Okay, so here there is an 8-bit instruction register which is used to store the instruction. So how ALU knows it need to be added? So fetched instructions is decoded by the instruction decoder as shown. So first the instruction is fetched and then it has to be decoded, right? Instruction need to be fetched and instruction has to be decoded like instruction decoder and machine cycle encoding. So these are all the internal micro level operations. So the instructions need to be fetched and after fetching it has to be decoded and after decoding it will understand there are two data available in the accumulator and temporary register. So I need to add it and store the result back in the accumulator. So after fetching the instruction and after decoding the instruction, it will execute the instruction. So three parameters which we have to remember forever when we talk about microprocessors: fetching, decoding, execution. That's very interesting. So fetching means what? Instructions are fetched from the memory to the instruction register. Decoding means what? From the instruction register, it will try to understand what I have to do with instruction, something like that. Decoding means what? Trying to understand. Execution means what? After understanding, action. Action is execution. So fetching the instruction, decoding the instruction, and executing the instructions are the three steps which need to be followed any microprocessors in the world. It can be 8085 or it can be Intel Core i9. Fetching, decoding, and execution is happening. So fetching is called as booting with respect to our PC. Fetching all the instructions and keeping it as RAM is called as booting. And OS is nothing but the instructions. So instructions are fetched from the RAM, which is called as OS in our case. So though based on those instructions, it is decoding and then it is executing. Okay. So here we are seeing only one arithmetic operation, which is addition. So like this, several million arithmetic operations and logical operations will happen inside the Intel Core i7 processor or i9 processor based on the user's need. And for the user friendliness, the outputs are visible in the screen, like how do we see in the alphanumerical display. After necessary code conversions and after necessary processing. It's fantastic, right? So fetching, decoding, execution. These are three magic words we have to remember forever. After decoding the microprocessor will understand what to do, then it will execute instructions as instructed. So execution means it will be executed through timing and control unit. There is something like timing and control unit I will show you. You can see there is something like timing and control unit you can see. So now the architecture is keep on increasing, right? It's very interesting. So this is your ALU and this is your accumulator and temporary register. And this is the instruction fetching, instruction decoding. And after decoding, it will do the necessary actions by sending out the read pin, write pin, address/enable pin, input output memory pin, reset out, and all those pins. Because based on the instructions, this timing and control unit will do the control. That means control means what? Fetching, bringing the first data to the accumulator. Then second instruction will be fetched, and based on the second instruction, second data will come to the temporary register. And the third instruction is fetched. Third instruction will say, okay, please add the content of these two registers like that. And after adding, the result will be there in the accumulator. Then store back the result from the accumulator to the memory, something like that we can do. That's very interesting, right? So we'll see an example for your better understanding. Okay. So this is what the overall picture of any microprocessor. So there are arithmetic logic units and there are registers. There are instruction registers, instruction decoders, and timing and control unit. With all these things, the processing will happen. Because of these modules, the digital electronics will become programmable digital electronics because there are instructions. This you will understand now very clearly. So your digital programmable devices which fetches, decodes, and executes the instruction and complete the operations as per the instruction. So the instructions are stored in DRAM memory, data are stored in random access memory. It's very interesting. So after fetching and decoding, timing and control unit inside the microprocessor do the timing and control actions to work for that instruction. If the instruction is to bring the data to the accumulator, then the data will be brought to the accumulator through the internal data bus as shown. So this is very interesting and very clear description. Timing and control unit is performing the execution part, as like how we discussed. Now let us take the Ad50 microcontroller addition example, and from this you can make much more clear understanding about how the arithmetic operation is performed in our microcontroller, what we are discussing in our syllabus. Here you see the first column is program memory, because as we all know, the instructions are stored in read-only memory. So read-only memory is called as program memory when we come to the microcontroller. So these are all the address 0x. As you look at the first column, look at the screen, look at the cursor. Humble request to all of you. This is very, very important. Please look at the screen, look at the cursor. The first column in the table is the program memory, which is 16-bit memory. So 0000, 0001, 0002, 0003, 4, 5. These are all the memory locations of the program memory. We talked about the instruction. No? These are all the instructions and data. So 74 is an instruction. 74 is an instruction. So this is called machine language or opcode. 74 means again it is binary, right? 0111, 0100. 0111, 0100 is the instruction. What does the 74 says? 74 is denotes MOV A, #2. What is MOV A, #2? Move the immediate data to the accumulator. Whenever you see the symbol hash, that indicates immediate. This we call as immediate addressing. So there is something like addressing mode. So now we are using this immediate addressing mode to bring the data to the accumulator. This is very important. So this is for us, for human being to understand. Move A, #2 is the human being to understand. How the 8051 microcontroller will understand? For MOV A, 2 means it is 74 is the opcode. What is opcode? Operating code. So this is the instruction. So this 74 is an instruction which is fetched by the instruction register as shown here. So the 74 will come here, and after decoding, so 74 is fetched, 74 is decoded, and after decoding it will understand. After decoding it will understand. Okay, immediately we have to move this 2 to the accumulator like that. 2 will come to the accumulator. That means in the next location, so in the first location 2 is available, copy this 2 from the memory and then paste it into the accumulator like that, it will do the operation. This is 2 byte instruction. Why? Because 74 is an instruction, and because it is immediate, immediately the next location some data is there, copy this data and then paste it in the accumulator, something like that you need to understand. Okay, so please try to understand. The first column is the address, second column is nothing but the machine language, where how a microcontroller can understand. 100% I know, you know, we cannot understand the second column. So to make us to understand the second column, third and fourth column is there. That is very important. The second column is the only column where the machine will understand. What is the machine? Machine here is microprocessor or microcontroller. With respect to this table, the machine is microcontroller, which is 8051 microcontroller. So this is the language of 8051 microcontroller. So when you give 74, 8051 microcontroller can understand. I have to move the next location content to the accumulator like that. So this we human being can understand by this third column and fourth column, which is called as assembly language. Third column and fourth column is called as assembly language. This is for human being to understand. And the second column is called as machine language. The first column is the memory location where these instructions are being stored. Now 74 is an instruction, 2 is a data. The first instruction is over. That means we have moved the immediately the number 2 to the accumulator. Yes or no? What is the second instruction? Add A, 4. Meaning what? Add the content of accumulator with the immediate constant 4. It is very important. Add the content of accumulator with the immediate constant 4. Hash means it is immediate. This is for human being to understand. How the 8051 microcontroller will understand? By fetching the instruction 24 and by decoding the instruction 24, it will understand, oh, I have to add the content of the accumulator with the next memory location content. And I have to store back into the accumulator like that. It will understand by fetching, decoding this 24. And it will execute. While executing, it will add the content of accumulator, which is 2, with the immediate constant, which is 4, and the sum will be stored again back in the accumulator, which is 6, as discussed. and the sum is available in the accumulator, and then you have to copy from the accumulator, and then we have to bring out to the memory. For that, we are writing some instruction called MOV 04, A. What is that? Move the content of accumulator to the memory location 4, fourth memory location. So in accumulator we have 6. The 6 will come to the memory location 4 of our data memory. Memory location 4 of our data memory. This is for us to understand how your microcontroller will understand by fetching F5. By fetching the instruction F5, and after decoding the instruction F5, microcontroller will understand, oh, I have to copy the content of accumulator and then I have to paste it into the fourth location of data memory, because data memory is rewritable memory. Okay, so the fourth location of data memory, we will write back the sum. That is what given in the comments, as we all know. Okay, so I will demonstrate now. While demonstrating, you will understand much more clearly. So org000, this is called as assembler directive. So don't worry about it, the screen and all. I will make you to work with this Keil IDE, as we have discussed now. This is a Keil integrated development environment. With the help of Keil integrated development environment, we can simulate the programs. Now don't worry, I will simulate it for you. What we have seen in this table, right? What we have seen in this table, I have written it. Move a, #2. You see, move a, #2 is the instruction which is given. That is what we written here. Add a, #4 and move 4, a. And there is one instruction called short jump here, because as we all know, microcontroller has to be in while loop, no? So to make it while loop, no, it has to work, it has to run forever. That's why short jump here. This is the label short jump here. Here is this. So the program execution, I keep on executing the 6th line. Program execution is keep on executing the 6th line, because once addition is over, so it has to stop. So to stop this, it is working like this. Okay. F5 paranga, MOV data address, A. Data address is 4. Data address 4. Fourth data address is accumulator content போயிரணும்னா F5 னா அது புரிஞ்சுக்கும். இது டிக்ஷனரி. இதுதான் டிக்ஷனரின்னு வெச்சுக்கலாம். இந்த மூணாவது காலம் நாலாவது காலம் நமக்கு புரியுது. இந்த ஃபர்ஸ்ட் காலம் தான் மைக்ரோ கண்ட்ரோலருக்கு புரியுது. அப்போ மைக்ரோ கண்ட்ரோலருக்கு புரியுற மாதிரி எழுதணும்னா இது. அப்போ இந்த அசெம்பிளி லாங்குவேஜ் டு மெஷின் லாங்குவேஜ் கன்வர்ஷன் வந்து ஆட்டோமேட்டிக்கா உங்க IDE பண்ணிடுது. I think 200% I have answered Rajkumar's question, I believe. Fantastic question. Is Rajkumara? Rajkumar, I hope I have answered your question, right? Again, coming to Srihari, sir, last, yes, sir, thank you, okay. Sir, last before slide, 2 is given in opcode. How to differentiate between instruction and opcode? Instruction and opcode both are same, Srihari. 2 is given in the opcode. Last before slide. 2 is given in opcode. இந்த 2ங்கிறது data. 74ங்கிறது opcode. So 74ங்கிறது instruction, இது 2 byte instructionங்கிறதுனால 74 fetch பண்ணி decode பண்ணனும்னா என்ன தெரிஞ்சுக்கும் மைக்ரோப்ராசஸர்? ஓ, அடுத்த லொகேஷன்ல என்னமோ ஒரு டேட்டா இருக்குது, அந்த டேட்டாவை எடுத்துக்கொண்டே அக்குமுலேட்டர்ல வச்சுக்கணும்னு புரிஞ்சிருச்சு. அப்ப இது இன்ஸ்ட்ரக்ஷன். இந்த இன்ஸ்ட்ரக்ஷனுக்கு தேவையான டேட்டா அடுத்த லொகேஷன்ல இருக்குது. இந்த இன்ஸ்ட்ரக்ஷனுக்கு தேவையான டேட்டா என்ன? 2. இங்கதான் நம்ம சொல்லியிருக்கிறோம் 2 அப்படின்னு. அப்ப இந்த 2 எடுத்துட்டு போய் இந்த அக்குமுலேட்டர்ல வைக்கணுங்கிறது இது புரிஞ்சுக்கும். ஸோ இப்போ ஒரு இன்ஸ்ட்ரக்ஷன் கம்ப்ளீட் ஆகிறது. இது ஏன் 2 பைட் இன்ஸ்ட்ரக்ஷன் சொல்றோம்? 2 பைட் இருக்கிறதுனால 74ங்கிறது அக்குமுலேட்டருக்கு மூவ் பண்ணணுங்கிறது புரிஞ்சிருச்சு. எதைய மூவ் பண்ணணும் அப்படின்னா அடுத்த லொகேஷன் இருக்கிற ரெண்டை கொண்டே அக்குமுலேட்டர் வை அப்படிங்கிறது. இது 0th லொகேஷன் ஃபர்ஸ்ட் லொகேஷன் சேர்ந்தது தான் ஒரு இன்ஸ்ட்ரக்ஷன். ஒரு வேலை முடிஞ்சிச்சு. அடுத்த வேலை என்னங்க? 24. Fetching the instruction 24. After fetching the instruction 24 and after decoding, it will understand, oh, அடுத்த லொகேஷன் என்னமோ இருக்குதாமா, அடுத்த லொகேஷன் என்னமோ இருக்கிறத A கூட ஆட் பண்ணி ரிசல்ட் அக்குமுலேட்டர்ல வச்சுக்கங்கிறது புரிஞ்சிருக்கு 24. அதனால அடுத்த லொகேஷனுக்கு வந்து இந்த 4 எடுத்து கொண்டு போய் அக்குமுலேட்டர் இருக்கிற 2 கூட ஆட் பண்ணி சம்ம 6 ஆன்சர் ஸ்டோர் பண்ணி முடிக்க வரைக்கும் இந்த இன்ஸ்ட்ரக்ஷன். அப்போ செகண்ட் மெமரி லொகேஷன், தேர்ட் மெமரி லொகேஷன்ங்கிறது ரெண்டாவது இன்ஸ்ட்ரக்ஷன். சரி, இது முடிச்சோடனே மூணாவது இன்ஸ்ட்ரக்ஷன் என்ன? F5. அப்போ F5 is an instruction which is fetched by the microprocessor, and then after decoding it will understand, ஓஹோ அக்குமுலேட்டர் இருக்கிறது கொண்டு போய் 4வது மெமரி லொகேஷன்ல வச்சுக்கிற மாட்டிருக்குது அப்படின்னு சொல்லி புரிஞ்சுக்கிட்டு இந்த முடிஞ்சு. அப்போ இது பேர் எல்லாமே மூணுமே 2 byte instructions. There are 3 instructions which are all 2 byte instructions, where 74, 24 and F5 are the instructions. 2, 4 and 4 are the corresponding data. are the corresponding information added, value added information. அப்படிங்கிறது 100% புரிஞ்சிருக்கணும். Siranjeevi's question, what is the difference of using small and caps A? There is no difference, Siranjeevi. So capital A யூஸ் பண்ணிக்கலாம், small a யூஸ் பண்ணிக்கலாம். இங்க add a, 4 அப்படின்னு small a யூஸ் பண்ணியிருக்கிறேன். பட் நம்ம PPTல capital A யூஸ் பண்ணியிருக்கிறோம். Capital A and small a doesn't matter. Okay, so it is not case sensitive in some cases. In this case it is not case sensitive. இது capital A போட்டுக்கலாம், small a போட்டுக்கலாம். பாருங்க ரெண்டு பேர் பாருங்க, 4th லைன்ல small a போட்டுருக்கோம், 5th லைன்ல capital A போட்டுருக்கோம். So both capital A and small a is acceptable by this compiler. That's all. Based on the acceptance, we can make use of it. That is the one thing. Okay, I think I have answered Siranjeevi. Siranjeevi, did I answer the question? There is no difference between small a and capital A. Coming to Rajkumar, why for the same instruction move there is two opcodes, 74 and F5? Okay, fantastic question. Wonderful question, Rajkumar. Why for the same instruction move there are two opcodes, F74 and F5? This is very interesting. MOVங்கிற ஒரு இன்ஸ்ட்ரக்ஷனுக்கு 74ம் இருக்குது, MOVங்கிற இன்ஸ்ட்ரக்ஷனுக்கு F5ம் இருக்குது. இந்த கேள்வி ரொம்ப கவனமான கேள்வி, ரொம்ப அருமையான கேள்வி. which is MOV A, hash data இருந்ததுனால இங்க 74 இருந்துச்சு. இன்னொன்னு F சொன்னீங்க இல்லையா Hare Krishna sir, after the simulation 6 moves to data memory but still the accumulator holds the 6. What will be when it will be deleted? நல்ல கேள்வி Hare Krishna. நம்ம எப்பவுமே இந்த மைக்ரோ ப்ராசஸர் என்ன பண்ணணும்னா Control C Control V தான் பண்ணணும். காப்பி பேஸ்ட் தான் இது, Control X Control V கிடையாது. நம்ம லாங்குவேஜ்ல சொல்றேன், ஐ ஹோப் Hare Krishna can understand this. இது Control X Control V, கட் பேஸ்ட் இல்ல, காப்பி பேஸ்ட் தான். அது ஃபர்ஸ்ட் क्वेश्चनக்கு ஆன்சர். செகண்ட் क्वेश्चनக்கு ஆன்சர், அந்த R எப்பங்க ஓவர்ரைட் ஆகும்னா அடுத்த இன்ஸ்ட்ரக்ஷன் ஏதாவது வரும்போது ஓவர்ரைட் ஆகும். Until it is being overwritten by the next instruction, the content will be there in the accumulator or in the corresponding registers. That is the answer, Hare Krishna. And thanks a lot.